Welcome back everyone, and let's just finish this chapter today with the last two factors that can affect reaction rate, which are temperature and catalyst. So we're going to look at dot point 7.4 and 7.5 today. So just a quick recap of what we did last lesson. We looked at collision theory and how we can use collision theory as a theoretical framework to explain different ways to increase reaction rate. So there are three conditions in collision theory. The first one is that reactants must collide, and the second one is that reactants must collide with the correct orientation. And we've discussed how we can increase the reaction rate by increasing the frequency of collision by either increasing the surface area, the concentration, or the pressure of the reactants, depending on the states of the reactants. The other condition is that reactants must collide with enough energy to overcome the activation energy barrier. And I think we've talked about this last lesson as well. If you want to increase the amount of energy that reactants have, that's one way to make sure that more reactants can collide with enough energy to overcome the barrier, or you can lower the activation energy barrier. So the first way, which is to increase the energy of the collision, this is by increasing temperature. Whereas you can lower the activation energy barrier if you have a catalyst. So we're going to talk about these two methods in a little bit more details today. So before we start, let's just talk about the idea of kinetic energies, particles. So I have, I think, 15 particles here. And if you have particles in a closed system, such as a reaction chamber like this, you can see that obviously particles move all the time, but they also don't move at the same speed. So when you have a mixture of particles, they will move at different speeds. And if you follow any one particles, the speed that they're moving will also fluctuate over time because they come into contact with other particles. However, what our scientists have done, actually mathematicians, is try to come up with a way to represent the average kinetic energies or the average distribution of kinetic energies of particles. So if I have 15 particles, for example, and let's say this is the kinetic energy on the horizontal axis. Now you can label this as kinetic energy. Some textbooks may label it as speed of particles or velocity, but essentially we're talking about how fast they're moving. Then maybe you're going to have a distribution like this across the kinetic energy scale. So in theory, you don't have any particles at zero kinetic energy. The exception, of course, is if you are at absolute zero, but it is not very realistic. So this is an example of the distribution of kinetic energies of the particles. So the particles will cover a range of kinetic energies, and maybe you have some moving really slowly and some moving really quickly, and then the majority of them will probably move around these particular kinetic energies. So if I connect these, I can actually make a shape out of this distribution. In reality, you probably don't have just 15 particles in a mixture. You're definitely going to have a lot more than that. But you're going to have a curve with this characteristic shape. And this is called the Maxwell-Boltzmann energy distribution. And it is a graph that describes the distribution of energies of particles in a mixture. But it always takes this characteristic shape. So in order to explain the effects of temperature and catalyst to reaction rate, we need to first understand the Maxwell-Boltzmann energy distribution. So this is the graph again. You're not going to have to draw like the 15 particles when you draw the Maxwell-Boltzmann distribution. I just want to show you what it is trying to represent. So the area under the curve essentially is a representation of the amount of particles in the reaction mixture, and most of the particles will be around here. A few of them will be moving really slowly and a few will be moving really quickly. And the horizontal axis is, sorry, the vertical axis is the number of particles with a given speed. I just really like to say Maxwell-Boltzmann energy distribution, but that is the name of this curve. So it shows the distribution of particle kinetic energies. Small fractions have either very low, very high velocities or kinetic energy, depending on however way you want to call it. We normally just stick with energy just to make it consistent because it has the word energy in the name anyway. But the bulk of the particles will have intermediate velocities. or kinetic energy. Now, for anyone who has done methods, actually, I don't even know whether the methods people can pick this up, but this is actually a probability distribution. This is the continuous random variable, and this is the function if you want to. If you really like maths, I don't know, exponential just makes me happy sometimes. But you can see here that this is actually a function of temperature. So this graph is specific for a specific temperature. If you change the temperature, you will change the shape of the graph. And no, you do not have to memorize this. I would like to, but you don't have to. So the other thing with the Maxwell-Boltzmann energy distribution is that you can actually represent the activation energy on this curve, and you can sort of see how many particles actually have enough energy to overcome the activation energy barrier, which is not something that the energy profile diagram could do. So if this is the distribution of energies of all the particles in the mixture, then normally the activation energy will be around here. So normally it's actually quite hard for a chemical reaction to happen. So only the particles on the right side of the activation energy would have enough energy to react. Any other particles on the left side, basically the collision is not going to be successful because the collision is not strong enough to break the bonds of the reactants. So if I go back to my original scale here, maybe only these two particles. So if this is the activation energy, potentially only these two particles could lead to a successful collision, given that they meet the correct orientation, of course. But the activation energy normally is around here for a reaction. Okay, so once you have the Maxwell-Boltzmann energy distribution, you could use it to predict what happens to a mixture when, let's say, you increase the temperature. So this is just the distribution again from before. So we'll assume that the activation energy is going to be around here. So I'm just going to abbreviate it to EA. So particle moves. I just like to do animations if I can. Now let's say I increase the temperature, which I did here, and you can see there's an increase in temperature here, and naturally particles move faster. But at the same time, not all of them will move faster. Like some of them are still moving quite slowly, and it really depends. So if you need to do another distribution, it's probably going to look like this. So the majority of the particles sort of move faster, but you probably still have some particles that are moving very slowly, and you have some that are moving very quickly. So if we do just a quick shape of the graph, so this is the original shape, and now I'm increasing the temperature. So let's say it looks like this. So it looks a little bit more like a normal distribution, but obviously this is an example and you're never going to have exactly 15 particles. However, the one thing that has changed is the proportion of particles that meet the EA has now increased from 2 in the first case to 3 in the second case. So this is why there is an increase in the reaction rate, because more particles can now overcome the activation energy barrier. However, the area under curve remains the same because you still have 15 particles in both situations. So just increasing the temperature, you're not increasing the amount of particles. So the area under curve remains the same. Okay, so this is one thing that I really need to emphasize when you draw the Maxwell-Boltzmann energy distribution with a higher temperature. Normally it probably has a nicer peak. It's probably not going to be this symmetrical, but anyway, I only have 15 particles to work with. So this is higher temperature. When you have to show the change in the Maxwell-Boltzmann energy distribution, when you increase the temperature, make sure that you draw it in a way that it looks like the area under curve stays the same. You don't have to do calculus to actually calculate the area under curve. You just want to kind of make it look like it's not just increasing. So this is a representation that you will see a lot in your textbook. So obviously, once again, you don't have to do the actual calculations of area under curve, but an estimation. So if you are widening the curve, then basically the peak has to lower so that the total area doesn't change. And you can see how there is an increase in temperature from, in this particular example, 0 to 1,000 to 2,000 degrees, and that is going to change the shape of the energy distribution, which is why this curve is specific to a temperature. So I think this is just what I just said. So temperature increase will increase the average velocity as well as the spread. So anyway, the area under the curve remains the same. So this is how you could explain the effect of temperature. Increasing temperature, it increases the kinetic energy of particles. So let's say if, for example, the activation energy is around here, then obviously in this case, you don't have any reaction at 0 degree because none of the collisions in this case meet at 0 degree would meet activation energy. But when you get to 1,000 degree, you get all of the particles on the right side of the activation energy could now lead to a successful collision. And if you get to 2,000 degree, then more particles could actually lead to a successful collision. Okay, so if you need to explain the effect of temperature on reaction rate, so this is just a recap of last lesson. Obviously, increasing temperature would increase the frequency of collision because the particles are moving faster. So temperature is interesting because it affects both frequency of collision as well as the energy. So this is just from last lesson. It increases frequency of collision, so there is a higher chance that the particles would collide with correct orientation. However, more importantly, it would increase, and the key word to use here is proportion. So it will increase the proportion of particles. And the reason why we use proportion is because we're talking about the portion of the area that is increased. So it's not the, I don't think number, well, it's not wrong, but it's not the best word to use in this situation. You're trying to explain that the percentage of this curve that now is on the right side of activation energy has increased. So the proportion is the word that we use most of the time. So this increases the proportion of particles having enough energy to overcome the activation energy barrier. So temperature is the only change that would affect both frequency of collision and proportion of particles meeting activation energy. But the effect on the activation energy is actually the most significant one. So more importantly or more significantly, this is really important. So if you need to explain why temperature increases reaction rate, you have to talk about the second point of it increasing the proportion of particles meeting activation energy barrier. Okay, so I'm just going to update this chart, which I think I showed you last lesson. So there are two ways to increase reaction rate. You either increase the frequency of collision or increase the proportion of collision with sufficient energy to overcome the activation energy barrier, and temperature is the only one that affects both, but it affects the proportion part a lot more significantly. So that is it for the temperature video.